When you string a heavy cable between 2 points, gravity and tension pull it into a very specific, perfectly symmetrical shape. To analyze this mathematically, we plot the parabola on a Cartesian plane. Its default equation is standard form. F of x equals ax squared plus bx plus c. The most structurally important locations here are its lowest point, the vertex, and where it crosses the horizontal axis, the roots. But the standard form equation does not give us those coordinates. The values for a, b, and c represent a sequence of algebraic operations, not geographic locations. While the constant c identifies the y-intercept, the coefficients alone leave the coordinates of the vertex and the roots hidden within the algebra. To see the geometry, we have to translate the equation into one of two specialized formats. First is intercept form. The equation is factored so values p and q directly map to where the parabola intersects the x-axis. Second is vertex form, where variables h and k explicitly state the coordinates for the curve's absolute peak. The challenge is getting there. We have a flat sequence of added terms, ax squared plus bx plus c, and we need to compress them into a tightly grouped squared expression. We achieve this translation using a specific algebraic technique called completing the square. Here is our standard form equation alongside its geometric curve. To reveal the vertex, we start by separating the x variables. Factoring out the leading coefficient a exclusively from the first two terms isolates the variable structure inside a parenthesis. Our target format relies on a perfect binomial square, an expression that looks like p plus q all squared. We need the terms inside our parenthesis to match this exact structural pattern. To force that pattern, we look at the inner coefficient, b over a. We divide it in half and square the result. This calculates out to b squared over 4a squared. Algebra demands balance. We cannot simply add a new value without changing the equation's total worth. So we must simultaneously add and subtract this term inside the bracket. By injecting this net zero sequence, we have built the exact mathematical scaffolding that is required to compress the equation. The first three terms inside the parentheses now form our perfect square trinomial. To isolate them, we take the subtracted fourth term, multiply it by the leading coefficient a, and push it entirely outside the bracket. Now we can collapse that underlined trinomial into a single squared expression. The structural transformation is complete. This new arrangement directly mirrors vertex form. The term inside the squared bracket aligns with h. This tells us the exact x-coordinate of the vertex is negative b over 2a. The external constants align with k. The exact y-coordinate is c minus b squared over 4a. We now have a direct translation. You can pinpoint the exact geographic center of the curve using nothing but the original standard form coefficients. Now let's run a real set of numbers through this logic to see exactly how it operates in practice. We have a standard equation, y equals 3x squared plus 6x plus 9. Our goal is to find its absolute minimum. We execute the complete the square steps, factor out the 3, calculate the missing term, and both add and subtract a 1 inside the parenthesis. Condensing the trinomial yields vertex form, y equals 3 times x plus 1 squared plus 6. The coordinates of the vertex are negative 1, 6. We can bypass that long algebraic manipulation entirely by plugging our initial 3, 6, and 9 coefficients straight into our derived shortcuts. For the x-coordinate, negative b over 2a becomes negative 6 over 6, which is negative 1. For the y-coordinate, plugging the coefficients into our k formula outputs exactly 6. Both methods yield a vertex of negative 1, 6. The derivation holds true, providing a guaranteed shortcut to extract the hidden vertex from any quadratic equation. Finding the center of the parabola is only half the picture. The other crucial markers are the roots, the exact coordinates where the curve intersects the horizontal x-axis. For any graph, an x-intercept occurs under one strict condition. Its vertical height, the y-value, equals exactly 0. By setting our derived vertex equation to 0, we just need to isolate x to find those crossing points. We shift the constant term to the other side of the equal sign and divide the entire equation by the leading coefficient a. To pull the x variable out of its parentheses, we take the square root of both sides. Because squaring a positive or a negative number yields a positive result, this operation naturally forks into two separate paths, a plus and a minus. The resulting quadratic formula represents the vertex form solved for 0, a direct path to finding the roots of the equation. Look closely at the specific mechanism trapped under the square root, b squared minus 4ac. This expression is called the discriminant. It controls a hard mathematical constraint. In real geometry, taking the square root of a negative number produces no real solution. If the discriminant evaluates to a positive number, the plus or minus symbol functions normally. The formula outputs two distinct values, confirming the parabola slices through the axis twice. If the discriminant evaluates exactly to 0, adding or subtracting 0 yields a single answer. The vertex is resting perfectly on the axis. And if the discriminant is negative, the calculation stops. A negative under the root means there are no real solutions. Physically, the parabola is floating above or below the axis, never making contact. The discriminant acts as an immediate reality check, telling us whether the geometric curve even has roots to find before we attempt to calculate them. We have used algebra to uncover the geometry. Now let's run the engine in reverse and build a complete equation entirely from physical coordinates. Looking at this Cartesian plane, we know a parabola has its vertex exactly at 1, 2, and passes perfectly through the origin at 0, 0. We drop those vertex coordinates directly into the h and k slots of our vertex form. This instantly builds the majority of our equation. To find the final missing variable, a, we substitute the origin point coordinates in for x and y. Solving that simple arithmetic reveals a equals -2. Multiplying out the completed vertex equation forces it back into standard form, giving us y equals 4x minus 2x squared. Completing the square provides total mobility. It is the mathematical bridge that allows us to freely translate between raw algebraic data and physical geometry.